Oh man, I am so bummed out right now. I just made probably the best video ever in the whole wide world in the history of mankind. And it didn't save in the right format, so here I am for take two. Look, here's my proof. Look at that. Look how awesome that is. Don't you wish you could have seen that video? But anyway, hopefully this one will work. We're here today talking about 7th grade math, a geometry standard, and today we're talking about rectangular prisms. What is a rectangular prism, you might ask? See the question mark? You might ask that. A box. Okay, think of a box. So here's how we're going to deal with this. I think a good way to learn about 3D objects is to actually have a 3D object. You could do this at home. Okay, in this case I've got a Pop Tarts box, but you can use any kind of box you want. The only tricky part is I would recommend planning ahead. Most of them have these lids, right, and the lids break into 2 pieces, sometimes 4 pieces. I would actually take the lid apart, take the little flappy things off, and staple it together, or tape it or something, so it's all one piece. That's kind of important. So anyway, today we're going to learn about surface area and volume. Surface area is the tough part, volume's easy, and we will get to that. First I need to cut this box, break it down. Okay, so I'm going to cut along one of the edges, and then I'm going to cut along a couple of other edges, and gradually the box just kind of opens up so I can lay it flat. When you lay it flat, what you really have is a net, and when you're dealing with math problems on paper, a lot of times that's what you get, is the net. Okay? It might be easier to see the net if I can draw the lines in where the edges were for you. Okay? Edge is actually a technical term, right? That's one of your vocab words probably if you're studying that. Edges, those are these things. They connect the faces and the bases. Okay, so as you can see, now that I've drawn the lines in, we've got 6 different surfaces on a rectangular prism. We've got, maybe this will be easier to see if we put it back together. Okay, we've got a top and we've got a bottom. Those are called the bases. Okay, base 1 and base 2, let's call them. The bases are those surfaces that you think of, that's what it's sitting on, right? The bottom of the box sits on the base. The rest of the surfaces are called the faces. Okay? Something that's important to note, even though we've got 6 different surfaces here, you really only have 3 different surfaces to measure, because we have congruent and parallel, opposites. Once again, if we put it back together, it's easy to see. The top is going to have the same measurements as the bottom. The front will have the same measurements as the back, and the 2 sides will have the same measurements. Okay? That's important to note. It'll save you some time. Let's do some measuring here. This looks like it's 9 centimeters across. And I'm going to round it off to 13. Okay? We don't need to get too complicated here. I'm using centimeters, by the way. Looks like I need one more measurement. Here's another 9. I'm going to check and make sure we have the correct measurements, because when I see 2 9s I wonder, oh, did I do this right? But yeah, as you can see, I have, if we just isolate this corner here, you should be able to see all three measurements coming out of one corner of a prism. So I've got the width, that's that face there. I've got the depth, which is for base 2, and I've got the 13. So you can see all three dimensions right there. And you might recognize this shape, right? When you're looking at these problems on a piece of paper and they try to represent it to look like a 3D box, you're usually looking at three sides, okay? But we've got congruent and parallel. Now all we do is multiply, well, for surface area, what we're going to do is we have to, it's the sum of the area of all faces and bases. Okay, basically all the 6 sides. So the toughest part is maybe keeping track and making sure you don't do something once instead of twice, etc. So, for example, right here, we've got 13 times 9. See that 13? That 13 is going to go all the way across. All of these faces are going to be 13 times something, because that's how tall it is, okay? Then, since we know this one is 13 times 9, we know that over here we're going to have another 13 times 9, because there are congruent and parallel sides here. There are 3 pairs of congruent parallel sides. Now, let's check this out. If we fold it back up, see how this 9 right here goes with this side. And so I'm going to have congruent and parallel over there. Okay, and this is important to see. This little intersection of the 3 sides down here. See how the depth, this 9 right here that I'm pointing at, translates to being here. It's kind of hard to see when it's laying flat. But that's the deal is, let's see if I can get this to, see, there's a 9, and when we put them together, see how that 9 is also that same measurement for that side? Keep that in mind when you're looking at these shapes and they're in a 2D version on your paper. Okay? Now right here I have 9 times 9, right, because you can see the 2 dimensions. And since that's a base, my other base will also be 9 times 9. So we're saving lots of time here by getting that we have congruent and parallel matching pairs. Okay? And notice that I only took 3 measurements. Sometimes you might think you're getting overwhelmed on a problem like this because, oh no, there's so many measurements I have to take. You only need to take 3 measurements. Okay, 3 measurements. It's a 3D object. That's all there are. There's only 3 measurements. There's no reason to measure everything on here, okay, unless you're just being extra thorough, because the D in 3D equals dimension, and as we've learned in class, definitely dimension is another word. It's a synonym for measurement. So it's 3D, it's 3M, whatever you want to call it. Okay, so let's show some work here. I'm going to circle all of the answers. 9 times 9, 81. We know we're going to have an equal and opposite 81 over there. Over here, 13 times 9 is 117, because it's 90 plus 27. And I know I'm going to have one over here, equal and opposite, right? Congruent and parallel. As it works out on this Pop Tart box, just by coincidence, that's 117 and so is this. So I've got all my answers circled, and I'm going to use this face right here to show my work. Okay, so I need to show subproblems. Those are the little problems that we put together to get the answer to a big problem. So I've got 117. I've actually got it 4 times. And, all right, there's the word and, plus sign. And I've got the 2 bases, 81 times 2. There we go. So that's 440 and 68 is 468. and 162, which looks like 630 centimeters squared. Square centimeters. All right. So, step by step, all we do is we take the three measurements, which you should be able to find by either doing this with a real box or visualizing where the kind of two of the faces and the base come together. That's where your three measurements are going to come from. Okay, three measurements. Then you're going to find the similarities between the faces and the bases. Like, for example, this 13 is how tall it is, so I put a 13 on all four of those faces. Okay, you're finding where the measurements match up with the other sides, like we did down here. This 9 down here matched up over there. Okay. Then we simply multiply two things, two measurements. That's why the little 2. Even though this is a 3D object, we're only taking two measurements in each case, right? Two measurements. There's two things, there's two things, and we're adding them together. So that's why this is really a two-dimensional calculation. So 630 square centimeters is how you say that. We've got faces. Oh yeah, this thing is called a net. That's when you see on paper what looks like what we created here, a broken down box, a flat thing. A net is a 2D version of a 3D object. Finally, we just need to do volume. Volume is how many cubes fit inside. Okay, so we're going to go to a piece of paper here. So, for volume, what are the three measurements? What are the three dimensions, if you want to think of it that way? Well, on our Pop Tart box, we have 9, and a 9, and a 13. All we do is multiply them together. Volume, so easy. You get 1,053. Since there were 1, 2, 3 measurements, you put a little 3 there. Simple. And we would say cubic centimeters as far as the correct way to say this or write it. Okay. Now some people get all caught up in, hey, what about the order these things go in? Does that matter, right? I have length, width, and height, or is it depth and width and length? What is it? What is it? Oh no, I'm going crazy. It just doesn't matter. It doesn't matter. Why? Because of our friend, the commutative property, which states that order does not matter, essentially. That's my unofficial definition. Simple example. 2 times 3 times 4. What do you get? 24. Mix them up. 4 times 2 times 3. What do you get? 24. 3 times 4 times 2. You guessed it. Since we're using all the same things, the same dimensions, it's the same. Remember that when you get to a complicated thing that has bigger numbers that maybe you can't do mentally, is don't waste any time, not even a second, worrying about what order to put them in. When you're dealing with the volume of a rectangular prism, you just find the three measurements and multiply them. That's it. Okay? Order does not matter. Multiply the three numbers, call it cubic centimeters in this case, and we are done. Man, I wish you still could have seen the first version of this video. It was 10 times better. But I think we got everything, and I hope that helps, and I will see you around. Thanks. Bye.